So thank you very much for the presentation. I'm Pietro, and today I'll talk about custom processing unit, reverse engineering and customization of Intel Microcode. I'm actually very happy to present this talk. And so in this talk, I'll present you custom processing unit, which is the first microcode framework for full CPU microcode static and dynamic analysis, all via software. So to understand what this framework is capable of, we should first understand how do modern CPUs work. And from a very, very high level perspective, we can imagine a CPU being divided between a front end and a back end or out of order execution engine. So the front end is the component that is responsible for fetching the instructions from memory, decoding them, and passing them to the out of order engine to be executed. So a very important term in my previous sentence is that the front end decodes the instruction. But why is that? So the backend is actually a very complex engine, but only able to execute very simple instructions, the so-called micro operations. So the front end will decode x86 instructions into micro operations that can actually be executed by the out-of-order engine and are much simpler. So in theory, like most of micro operations will be 1 to 4 micro instructions. Like, for example, think about, I don't know, memory read or arithmetic instructions. But there are a few instructions that require a very complex logic to be executed, and they are the so-called microcoded instructions. Think about if you want to execute CPU ID, for example, where you have a single instruction that can implement multiple functionalities depending on the input data that you pass. For example, multiple like query, for example, the, I don't know, CPU ID of the processor, actually the processor name. So you can have complex functionality that have to be implemented in hardware. And those instructions could be translated into like hundreds or even thousands of micro operations. So our work is based on previous work from Mark Helmholtz and his colleagues that were like incredibly cool work that were able to achieve the read and lock on Easdon Goldman CPUs. So the read and lock is a very interesting state of Intel CPUs where they basically enable to be debugged by an external debugger and have access to its internal components. So with the read and lock CPU, they were able to extract and reverse engineer the microcode format of Easdon Goldman CPUs. And while reverse engineering that, they discovered and documented instructions that were able to access internal buffers from software in case of read and locked CPUs. These two undocumented instructions that they were called udebug read and udebug write have read and write access respectively to internal buffers of the CPU. Like a few of them are just internal buffers used by the CPU, or for example, input-output ports, the power supply units. But very interestingly, those instructions have access to the CR bus or control register bus. And the control register bus is an incredibly important component inside our CPUs. So our CPUs use the control register bus to interact with most of the other internal components. So for example, if you execute a write MSR just by updating model-specific registers, those model-specific registers are actually like mapped as a command sent to the CR bus, actually an address to the CR bus. So most of them will be just mapped one-to-one to a CR bus address. But also control status registers are actually just like semantically modeled as an address in the control register bus. And most interestingly, the control register bus has a few addresses dedicated to control post-silicon validation features. This is a very interesting thing since post-silicon validation features are something that only silicon vendors are supposed to access, for example, to test the functionality of internal components, having full control of them. So this paper starts with the question, what can you do with access to microarchitectural buffers? And to understand what can we do, we have to understand how do, in general, microcoded instructions work. So let's assume that our processor is about to execute a CPU ID instruction. A CPU ID instruction is a microcoded instruction, requires a complex logic. So the microcode sequencer, that's the component that manages the microcode, will actually have to emit a stream of micro operations. So we can imagine as if inside the CPU there is some sort of lookup table or translation table that every time you're about to execute a microcode instruction, it redirects the execution to the microcode ROM, where actually all the microcode operation resides and can be fetched from the microcode sequencer to emit the microcode routines required to implement the actual instruction logic. But as the name says, the microcode ROM is a read-only memory. So if we only add that, then the microcode ROM, then the microcode inside the CPU will be mutable. And think about if you ever discover a security bug or even just a functionality bug, then you will need to update the microcode. And if that's the only read-only memory, you wouldn't be able to. So there is a second component inside the CPU, that is the microcode RAM, that contains patchable microcode operations that can be actually overridden with microcode updates. So only Intel is supposed to access the microcode RAM and patch them with microcode updates, but today is not anymore like that. And we can imagine there is another component that has to map a microcode ROM address to a microcode RAM address every time there is an instruction that has been patched, and then a better version of that microcode routine exists. So we can imagine there is this match and patch component that redirects the execution from the ROM to the RAM to execute the patches that have been installed inside the CPU. So if you look at the microcode, you can imagine how complex is that. There are like way more registers than they are at the x86 level. For example, temporary registers used to do temporary operations before you actually map the operation to the architectural level. There are different memory areas, there are different logics, and most importantly, microcode is heavily optimized for size. So the microcode RAM is pretty limited, and Intel has to pack as much as possible functionalities inside a limited memory area. So you will have all crazy kind of stuff, for example, basic blocks that are shared between different microcode routines, or even basic blocks that are, depending on the context, either used as an if-else branch or as a loop. So you have a high complexity at the microcode level. And our first improvement to the microcode world has been to design and map the semantics of all the microcode operations that we could understand actually, and implement a microcode decompiler. So we modeled the CPU behavior to map the low-level semantics of the microcode itself to a high-level semantics to provide the reverse engineering community a tool to reverse engineer microcode with much more ease. Then we can use our tool to understand the internal features of the CPU. And we started using our tool to reverse engineer how the CPU itself deals with the microcode, how it updates it, how it reads it, how it actually accesses it. And we know from the microcode that the CPU will access the microcode from the CR bus. So what we can do is, with our reverse engineering framework, we can look at the patterns that the CPU uses to access the control register bus and reproduce that same accesses using those undocumented instructions that have access to the control register bus. So we can use the undocumented instruction to provide like wrappers and high-level semantics to the low-level functionality of the control register bus. And in the end, we can use the undocumented instructions to control the microcode through the control register bus. So with CustomProcessingUnit, the idea is to leverage those instructions to patch microcode via software. So we can completely observe the CPU behavior since we have microcontrol, but we can also completely control the CPU behavior through the microcode. And all within a BIOS or a kernel module, since we can have those microcode instructions like affected from software thanks to the undocumented instructions. So our framework is able to patch, hook, and even trace microcode execution at runtime to give you a complete understanding or a deep understanding of our CPUs. So with microcode patches, we can fully customize the CPU behavior. So for example, you can change microcode instructions or even add novel functionalities to the CPU itself. In our paper, we show how you can use our framework both to improve the security and the performance of our CPUs through microcode customization. So for example, we provide the first implementation of pointer identification codes in the x86 world. bringing a very important ARM mitigation from the ARM world architecture to the x86 one. In the paper, we even show how we can leverage side channels to break pointer identification code, and then even provide a stronger version of pointer identification codes to the x86 world that is not subject to known side channels. We even show that with microcontrol, you can implement a novel breakpointing design. So we introduce fast microcode breakpoints, where the idea is to execute software breakpoints, but at the microcode level, so that you can avoid all the interrupt context switch that you would incur if you, for example, you were debugging software with software breakpoints. And we show how you can have up to 1,000 times faster breakpoint execution at the microcode level, and implement microcode routines, for example, to support fuzzing at the binary level through software breakpoint implemented at the microcode point. We even show with our framework how you can bring constant time software division, that is like a known mitigation, to the hardware. So we show constant time division in the hardware level at the microcode level that can improve the security and the performance of CPUs through microcode customization. With microcode hooks, you can literally install microcode to observe events inside the CPU. So you can just set up the match and patch mechanism to hook certain microcode location, collect your data and resume execution, for example, to build your own performance counter. But with microcode traces, you can do much more. So with microcode traces, we can leverage microcode hooks to set up hooks for every possible microoperation inside the CPU that just dumps the timestamp at which that microoperation has been executed, and then just by sorting those timestamps, reconstruct the microoperation that are executed at runtime inside the CPU. And with microcode traces, we leverage those to reverse engineer the secret microcode update algorithm from Intel, so that we have a full understanding of what are the rules, what are the encryptions, what are the signature schemes of the secret microcode update algorithm and how it works. We fully documented it, and we've performed the first public security evaluation of the algorithm. We even reverse engineer how microcode updates after being decrypted get parsed. And with our surprise, we discovered that the microcode update is actually bytecode. So the CPU, when it's installing a microcode update, is actually interpreting a bytecode or commands from the microcode update itself that teach him how to improve and update itself. So you will have commands to reset internal states, write different microcode values, send commands to internal components, and even control flow directives, making microcode updates a fully Turing-complete language. We developed a microcode decryptor and a parser for microcode updates, automatically collected all the existing updates for Goldman CPUs, decrypted all of them, and released them to the public so that they can be further analyzed. So to conclude, with Custom Processing Unit, we massively deepened the understanding of modern CPUs through microcode access. We presented a static and dynamic analysis framework for microcode that is able to compile, assemble, patch, and even fully trace at runtime our CPUs to let us fully control our CPUs. Our framework is open source, and if you have any questions, I will be happy to take them.
Thank you, Pietro, for the talk. Any questions? So if I remember correctly, the original work for getting read and lock requires some intricate access to the processor. With your framework, is it still required, or can we just generate microcode patches and use them as are?
So the starting point of the framework is a read and locked CPUs. So you need a CPU that is read and locked, in this case, the known read and lock for Goldman ones, and the known read and lock process for Goldman CPUs requires you to flash a custom BIOS. You can flash the BIOS either from software, if your CPU allows that, or from the hardware level with like a hardware flasher. After you flash the BIOS and then read and lock the CPU, our framework is fully software. So you just have to enable the undocumented instructions with a write MSR, and then you have full control of the microcode level from software, so no hardware is required.
Thank you.